Welcome back, folks. Time to get started with Module 10 now, and in Module 10 we're going to take another look at the states of matter, solid, liquid, gas, aqueous, all that good stuff, and reevaluate it a little bit with more of our understanding of how molecules are built. And later in the week we're going to look specifically at the forces they exert on each other after a Zoom session where we get a sense of how structure correlates to things like boiling point or solubility. But before that, we're going to take a look at the one situation where the forces are so weak as to almost not matter, and that is in the gas phase. The tricky thing about quantifying gases is that unlike the situation we have with pure substances that are solids or liquids, we can't very easily put them on a scale. If I take a balloon, particularly one filled, let's say, with something like helium, and I put it onto a postal scale or an analytical balance, I'm not going to register a mass here, because especially if it's something like helium, it's just going to float away. And the reason for that is because this gas inside the balloon, when it is indeed something like helium, is less dense than the air around it. So it's not that it doesn't have mass, it most assuredly has mass. If there are molecules in here, it's got mass. It's just that it's buoyant. It's the same reason you float when you dive into water. It's not because you don't weigh anything, it's just because you're less dense than the water. So of course that's going to make massing gases a little bit challenging. So what we generally measure instead is a quantity called pressure. And all that pressure is, in general, is a force exerted over an area. But to make that a little less physics sounding, all it is this. If I look at the interior wall of the balloon, take this right here and blow it up, at all times, I'm going to have molecules of that gas moving very freely. Remember, in the gas phase, they aren't generally up next to each other and moving past one another. It'll be moving nice and freely, and every now and again, a molecule strikes the wall of the container and bounces off. And if you know even just a little tiny bit about physics, you would know that if this thing reverses direction, it had to impart a force. It's the same thing if you were to run into a wall and bounce off of it, you would impart a force to that wall. Now the force of all of those molecules is going to be exerted over a certain area. And because the force the molecules generate is going to depend on things like how many of them there are and how fast they're moving, and because the area that they actually strike is going to depend on how much space they're taking up, pressure itself isn't a good measure of how much gas you actually have. In fact, to get at that, technically you need what's called the ideal gas law. And that ideal gas law will take into account things like how much space the molecules are taking up, how many of them there are, this N generally is moles, and how fast they're moving, which is the temperature, along with how much pressure they're exerting. R here is just simply a constant. You don't have to really worry about that, because we're not going to do any math with the ideal gas law. But the key takeaway here is that pressure is how we go about quantifying gases. Pressure depends on a lot of stuff. Pressure is actually something that we change on a moment-to-moment basis in certain parts of our body. And so it's worth getting a sense of how it's going to behave with respect to all of these variables. To the worksheet. If you remember back when we first introduced kinetic energy, temperature was something we said actually was a good measure of that. Technically, temperature is a measure of the average kinetic energy for the molecules in a sample, which means essentially it's a stand-in for the speed. We just talked about pressure being the ratio between force and area. And so what we're going to see here is there are two ways in general we can increase the pressure, and one of them is going to in fact be related to temperature. One way we can do it is we can increase the force. So in other words, more oomph hitting the walls. And since we said that the molecules generate that force that leads to pressure by colliding with the walls, that means that the two ways we could increase the force would be to have more collisions or harder collisions. In fact, if you think about this, these are also the ways that we got greater reaction rates. And so what that means here is that for more collisions, I would increase N, the amount of gas present, For harder collisions, I would increase T, which is going to mean speedier molecules smacking the walls harder. The other thing we can do is we can give them a smaller area to hit. And so this would say decrease the area. For our purposes, though, that usually comes along with decreasing the volume. So this can give us at least a few ideas about what we might need to do in order to increase pressure. And so with that in mind, we're going to do a few quick demonstrations to take a look at the three major one-on-one laws that gases follow. Now, Boyle's law is a law that is just easier to experience than it is to really talk about. So I've got my own gas sample right here. If you've got any balloons at home, I recommend you grab one too, pause the video, come on back when you're ready to do what I'm going to do. Okay, if you've gone off and done that, what I'm going to do is going to look a little strange. Make sure nobody's watching. I'm going to hug the balloon. And if I do that, if I press on the balloon here and hug it, the result is as I apply pressure, I will notice that the balloon gets a little smaller, but also that as the balloon gets smaller, it pushes back on me harder. You'll notice that immediately. As soon as you start trying to press, you immediately have to press harder to make it any smaller than that. So the pressure that opposes you, the pressure that the gas inside here is exerting on the walls of the container, is continuing to rise as you attempt to make it take up less space. Worth noting that the reason that it doesn't change its size just at random is because at this very moment, the pressure inside the balloon is in equilibrium with the pressure outside the balloon. That is, there are air molecules from the atmosphere striking this on the outside, there are air molecules that are trapped inside the balloon hitting it from the inside, and those forces are exactly canceling each other out. Now to take a look at laws involving temperature, we're going to head over to the kitchen. Okay, what we have here is a 500 milliliter Erlenmeyer flask. It currently contains about 500, maybe a little bit more, milliliters of gas molecules. And what I'm going to do is put this balloon, this sort of flexible membrane, on the top of it. And so the balloon at the moment contains almost no gas molecules, but the nice thing is it will expand because it's going to enforce a roughly constant pressure if something changes about the gas molecules movement inside. So I'm going to take this, place it on the burner that you see right here, and we're going to observe what happens as those gas molecules heat up. And after waiting a few minutes, we seem to have reached some kind of equilibrium, and we've got this extra volume of gas here now up at the top held in the balloon. Now that relationship we just saw on the stovetop between volume and temperature is referred to as Charles' law. We also have Gay-Lussac's law, which looks at the relationship between pressure and temperature. And I think we can imagine that if I had not actually put a balloon on top, if I had instead placed my hand over the top of that Erlenmeyer flask, I would have felt extra pressure. We kind of have a sense that that's why the balloon expanded anyway. As the molecules would heat up, I would expect them to move a little bit quicker, to hit my hand and the walls of the glass flask a little bit more forcefully and a little bit more frequently, and that my pressure would also in that case go up. So this leaves us with a smorgasbord of new relationships. We said with Boyle's law, pressure versus volume. What we observed was that when pressure went up, volume went down. When I hugged the balloon tighter, it got smaller. And by the same token, when I made the balloon a little bit smaller, the pressure inside of it went up. We call that kind of proportionality inverse. In other words, one goes up, one goes down. To represent that with an equation, the way we would actually do it most easily is to say that pressure times volume equals a constant. And you can see here, if this has to always be 10, if I make the pressure a big number like 5, then the volume has to be a small number like 2. If I make the pressure a really tiny number like 0.1, the volume has to be a very big number like 100. We're going to see the other kind of proportionality for these two, however. Gay-Lussac's law, pressure versus temperature. Charles' law, volume versus temperature. In each of these cases, we saw direct proportionality. I heated up the container, and I would have felt more pressure on my hand. I heated up the container, and the balloon expanded. That's what we call direct proportionality. And it's the case for each of these. In this case, if one thing goes up, the other thing goes up. If one thing goes down, the other thing goes down. And same deal down here. Now in this case, the way that I would write it as an equation is to say not that the product of the two is going to be a constant, but instead that the quotient of the two will be a constant. And that way, if I double this, the only way that I still wind up with the same constant is to also double the thing on the bottom. The only thing we have to watch out with temperature, though, is that there are 3 different temperature scales, and some of them can go negative, which wouldn't make a whole lot of sense here, because negative pressure and negative volume are not a thing. So we need to make sure we're using the right temperature scale. That temperature scale is called the Kelvin scale. It never goes negative. When it's 0 kelvins, that means nothing is moving anymore. And in order to get comfortable with this, we're going to need to go all the way back to chapter 1 and look at Fahrenheit, Celsius, and Kelvin side by side. All of that in the next video.